Okay. So now start showing my screen. Okay. Do you see my screen with AstroHub gates?
Yeah, we can see the AstroHub.
Okay, great. Today, last time I didn't have enough time actually to show you how to use these computational tools. So therefore, today I'm going to walk you step by step through the instructions, and I will show you how you can do this computations. Okay, so we start with this website here, astrohub.uvic.ca. Okay, and you go to this gray screen, public and outreach server. So I click it. Then here we have Mr. Hub. This is what we need. Spawn. Okay. Click this orange bar. Okay, so now you are here. You are on, as you can see here, astrohub.uvic.ca outreach web server. Okay, first thing you can click this square terminal to open terminal window. Okay. So yeah, so this is terminal window, and the command ls list shows what you have here. Also, this file manager window here on the left shows the same files, as you can see. Okay, so in order to do this computational work, you go to this user directory. You can either click it here, okay, then after user, you go to Scratch Outreach, double click left button, and here you see directories with different names. We can also go there using this terminal window, just cd change directory to user and Scratch Outreach. Okay. Then ls, you can see here also a list of directories with different names. So here you make, if you have not done this yet, you make a directory with your name, make dir. I'm going to use a directory with my second name, Pavel then here, because as you can see here, I already have a directory with name Pavel, this one. And in the directory Pavel, I have already done some work, and I will show you some results later. But when you are here for the first time, you don't have your directory, so therefore first you make a directory with your name, like this mkdir, Pavel then, or whatever name you choose for yourself. So now, as you can see, now we have a directory Pavel then. So I go there, Pavel then. So of course it's empty. And the first thing you should do, if on the left here, directories with different names, I go to my other directory with name Pavel. So you can see here there is a directory, subdirectory with name process seems template. Okay. And the first thing that you should do in your empty directory is just to make a copy of this template directory to your copy, like cp copy -r. This means copy directory with all subdirectories. So it's here outside, Pavel, I process seams underscore template. and copy it here, right? Takes some time, not a long one. And you don't have to do this right now. Okay, you can do this later while watching the video recording of this lecture. Okay. While it's copying, I will go to my second directory file then. It's here. Okay, you see, it's copying here. Okay, while it's copying, takes some time. I don't know why it takes so long. Yeah, so it's copied. Yeah, okay. Yeah. So now the path to working directory, as you can see, user. You don't have to use home user 2 times, just user scratch 14_outreach parallel them. And here I have a copy of this directory iProcess_sims template. It's also shown here on the left. If I open it, double click, okay, left button. So there are 2 subdirectories here. This is just a link to nuclear reaction data. So now let's forget until the next Monday about the second directory, weak process impact. It is used to run Monte Carlo simulations for uncertainty studies. We will talk about next Monday. Now our task is to learn. Your task is to learn how to make that snake curve that I showed you last time. Okay, so for this you will need to use this subdirectory process tools. If I click it, okay. So the notebooks as well as README files that you are supposed to use on AstraHub outreach server, they all have the suffix outreach in their names. So therefore, look for and use README files and notebooks that have outreach as a suffix in their names. So therefore, let me just again show iProcess sims template, iProcess tools, README outreach. So left button, right button, open with node editor with markdown preview. Okay, here. So this is your main README file that you should read, and it provides provides you with step-by-step instructions how you can do all these calculations. So therefore, let me just walk you through these steps. Okay. Yeah. Probably I have not said this in this README files. I don't remember it. I can't immediately find this recommendation. But let me go back to my directory here. And the first step actually here is for you to rename. Yeah, to rename this template directory with the same name but without template, right? This is important because in the notebooks that I will show you later, I assume that the path to results of your computations it has iProcess sims without template, right? So therefore move means rename. I just click it here and I just rename it. So I just delete template. Okay, so now I have just iProcess sims. Okay, so let's go here. It's missed, right? Oh, sorry. User scratch outreach file then. Okay, file then. iProcess sims, iProcess tools. Okay, let me close this and open again. Yeah. Okay. So now let me walk you through these instructions. Okay. So first, it just provides some description of directories, what they can be used for. Okay. Also, it explains also here in the description of directories. This README file explains why you have to do these steps, like make a copy of the directory iProcess sims template from my directory file. Right? This is just because you don't have access to NuGrid code. Therefore, I have prepared for you run directories with the compiled code. So you have just executable files. Therefore, you just copy them. So this is just explanation of this. Okay. It says because this repositories can be accessed only by NuGrid members, I have prepared this directory iProcess sims template containing copies of the weak iProcess impact and iProcess tools repositories in my directory file. Okay, on AstroHub outreach server, you can copy this directory to directory under your name dir. So this parameter, this variable name dir, will later be used in analysis notebook, in notebooks that you will be using to analyze the results of your computations. And of course, you will see, you will have to assign name dir, the name of the directory that you created for yourself. Okay. So so this is explains that what I've already done. I copied this process simply subdirectory into my name directory. Yeah, I copied it. I copied it with changing its name. Okay, so yeah, I process sims without template. Okay. The next sentence here is also important. It says that the directory iProcess tools has the subdirectories, two subdirectories to run subdirectories. Run iProcess tools and const xi and run iProcess one zone then. That should be copied to the parent directory iProcess sims, not template, but now without template, and can be used to run one-zone simulations of iProcess nuclear synthesis constant neuron density. So if I go back to my directory, okay, I go to now renamed subdirectory iProcess sims. Before it was iProcess sims template, okay, and I go to iProcess tools, as README file says, and in iProcess tools you can see I have to run subdirectories, this one and this one. README file also explains that your main iProcess run directory will be this one, run iProcess tools and const xi. And it uses a method of keeping neutron density constant that it is described in the iProcess tools notebook constant neutron density method. So you can check it. So let's go on the left, iProcess tools here, notebooks here. And it's called constant neutron density method. Okay, this one, constant neutron density. So this notebook explains the method that is used in this run directory. You can have a look at this prescription, but this is not necessary. But if you're curious, if you wanna know what method is used, you can go there. Okay, so now let's go back here. We are in iProcess tools, and you can see in iProcess tools there are two run directories, this one and this one. which I've shown here also. Excuse me, here. And as README file says, your main run directory will be this one: run iProcess tools and context. And in order to use it, you have to how it says, you have to copy it to the parent directory. Okay, so this means copy -r this directory, and parent subdirectory is 2 / okay. If I go to parent directory here, now this run directory here in iProcess sims as README file recommends. Okay, not iProcess sims template. Okay, I was already sent that just iProcess sims. Okay, so now those were just some preliminary steps about these directories. Now let's go to some useful instructions. Okay, so there are just a few instructions, 1, 2, 3, 4 instructions. Let's walk step by step through these instructions. The first instruction says in the run directories, first try to run the executable code ppn.exe to check that it works as API tool and doesn't put any errors. So I go here to my run directory. Okay, I see that it's here executable code ppn.exe. Right. Let me see if we can, yeah. Let me go there. Okay, and I just try to run this executable file. So let me just close this file manager window so that the terminal window will be just wider. Okay, like this. And now I try to run ppn.exe and to see if it works and doesn't report any error messages. Okay. Okay. Yeah, okay, that's it. We see that executable has run successfully without reporting any errors. This is just information about the calculations. If now I clear my screen, Ctrl-L, and let's check what I have. As you can see, I don't have many new files. Just which one is new? Okay. Okay, these are 2 new files. Okay. These are 2 new files, either myself 00494 and flux _00494. So these 2 files were just created by this ppn.exe code. Okay, now let's go back to README file. Okay, so it says we have checked that it works. We've done this. Okay, now this is also important. I mean, all information, of course, is important, but this is really important. It says the next sentence here in the instruction says that the number and the size of output files that this code produces, the code ppn.exe, depend on values assigned to the parameters IO level. IO means input-output, input-output level, IO level. This parameter, as well as parameters iPload flux option and decay time in the file ppn frame input. So if I go to the run directory, I find this file ppn frame input here. I open it. Yeah. Also, you can use here. I use the text editor Vim or VI. You can use Nano, try some other text editors. Yeah, but I will assume that you're familiar with Vim text editor, so VI. So I open this file. If you open the file, like you can see here, and you don't see the content of the file, right? In order to get rid of this, this is just feature of this AstroHub, all AstroHub series. In order to see something after you have opened the file, first press Command Control F, and then number one, Shift Shift G, not capital G. So let me go back. You know, if I open the file ppn_frame.input this file with directory vi, okay, and I don't see anything. So I click Control F, and then either one Shift G, capital G, or Control Control U, W. This Control F and Control W, this is this command that scroll file in VI editor. Control F, Control forward, up and down, actually, Control D, Control down. Now you can see the file. And as README explains, so there are three parameters in this file PPN framework input that control the amount of output data produced by PPN_exe: I/O level, iPlot flux option, and decay time. Okay. First, although the next sentence explains how the parameter I/O level controls output, let me start with the second parameter, iPlot flux option. Okay. Here, the default value of iPlot flux option is 0, and it is used in most cases. Okay, let's check what we have here. Here, as you can see in template directory, I have the value of parameter iPlot flux option equal 1. Okay, what's happening when it's equal to 1? Okay, so it says only if you wanna make plots of reaction fluxes in this notebook, analysis outreach. Only in this case, use the value of iPlot flux option equal 1, okay? Like it's here, iPlot flux option 1. So therefore, the first thing that you will have to do, okay, is to change the value of the parameter iPlot flux option 1 to iPlot flux option equal 0, because the value 1 means that so when the value 1 is used, the PPN_exe code produces output of a huge size. It's really big size because these files, flux files, they are very big. You can see they are very big. So, sorry, ls-l. So we can see one file has a volume of 7 megabytes. And if we have like 41,000 integration time steps, in this case we have about 500. But if you, for instance, have 1,000 integration time steps, then 7 megabytes multiplied by 1,000 will make 7 gigabytes. So therefore, this is a huge. This is the output of a huge size. So therefore, the first thing what you need to do is to change iPlot flux option from 1 to 0. So unless you really need this flux outputs, okay, this is the first thing. The second thing, now let's go back to the parameter I/O level. When we use I/O level 0 instead of I/O level 1, this suppresses the output of information about the calculations only to the screen. Okay, So if IO level equals 0 instead of 1, this will suppress the output information about the calculations only to the screen. Now let's see. Here we have IO level equal 1. Therefore, you could see the output of integration step by step on the screen. If I use 0, IO level 0, like this, okay, and if I go back and if I will run this code again, ppn exam, right? Now you won't see the output of step-by-step time integration on the screen. So you just have to wait about maybe less than 1 minute until the code execution is complete. But as you can see, there is no output on the screen now. So yeah, that's it. Okay, and we have just the final result. So now, without actually flux output, we can change this. This 00494. So you can see now there is no output of the flux. This file with flux, it was produced earlier at time 2219. Okay, and right now we have produced only this file. Okay, so now for this flux file, as I already said, contains information about all reactions, and the number of reactions here actually huge. It's about 70,000 reactions are included, and this information is used, as I said, in one of the notebooks to make a diagram of reaction flow. So therefore, let's not use the output of fluxes in most cases. Let's keep this just for certain problems. Okay, and the next file, ISO-MSF, with the same integration time step for 494, as follows from its name, ISO-MSF. It provides a list of mass fractions. MSF stands for mass fraction for all isotopes that are included in this nuclear synthesis computation. So if I have a look at this file, ISO-MSF, right? You can see it has 5,223 lines, which means that here we include about 5,000 isotopes, both stable and unstable. In this nuclear synthesis calculations, you should keep this number the same, don't change this number, okay? And as you can see, this is just a list of mass fractions. So the first column provides just the number of the isotope, okay, from 1 to 5,000 something. The second provides, let's take, for instance, helium-4 proton number 2, electric charge. Third column provides atomic mass for helium-4. Okay, and this is mass fraction, okay, for helium-4. Yeah. Okay. So now each time when you are done with your computational results, you can clean this directory from results obtained earlier using this short convenient shell script clean output. You just execute it /, which means this script is in the current directory clean. Unless, as you can see now, there are no isomass fraction or flux files. So you can use this clean output each time you need to clean your current run directory from previous results. Okay. So now let's go back to README file. So I explained you what parameter iPlot flux option 0 and 1 are used for, and what the values of other parameter IO level 0 and 1 are used for. And now the third parameter is called decay time. Okay? And this sentence explains that output files for each integration time step, which NuGrid readers in NuGrid, which are called cycles. So don't be surprised when you see, say, in Python notebooks that analyze your result, the word cycle. Cycle is just a synonym for integration time step. Okay. When we calculate nuclear synthesis, this means that we do integration of the reactions of nuclear kinetics, and for each time step, we produce new mass fractions, new abundances of isotopes. Okay, so therefore, output files for each integration time steps are saved in the run directory only in the case when decay time parameter is 0. If decay time is larger than 0, for example, decay time is equal 10 to the 9 in years, 10 to the 9 years, and this 1 billion years. Only in this case, only output files for the last computed time step or cycle will be saved with abundances of unstable isotopes decayed over the specified decay time. So non-zero positive value of the parameter decay time provides the time given for unstable isotopes to decay at the end of your nuclear synthesis computations. Okay, because often abundance anomalies that we see in stars were produced in some other stars in the past, which means that there was enough time between the production of unstable isotopes and the isotope that we see in the given star for them to decay. Okay, so therefore, very often we need to give our calculation some reasonable decay time. So therefore, 1 billion years is a reasonable decay time, which means that during this time, most unstable isotopes will decay, except very long lived. There are a few of them. Okay, but decay time, as this text explains, also controls the output. When decay time is positive, then only the mass fractions for the last computed time step of cycle with decayed abundances will be saved. While when decay time is 0, undecayed mass fractions, undecayed abundances will be saved for each integration time step. And this difference is important because if you want to see how abundances change with time, right, during computations, then we want to use the parameter value decay time equals 0. Otherwise, we will have only the very last mass fractions for the very last integration time step. Let me show you how this works. Okay, let me go back to my run directory, and I open again this ppn underscore frame input file. Okay, and this is decay time, right? This is decay time. Now the decay time was positive, 1 billion years, and therefore you could see that only mass fractions and the flux file for the last computed integration time step was saved. So now I change it to 0, okay, to 0, and save and run the code again, right, with 0 decay time. I'm still using IO level parameter equals 0, so that therefore there will be, I think there will be no output on the screen. We'll just wait until the code execution is complete. Yeah, the code execution is complete. Now let's check what we have in the run directory. Because I use decay time 0, I expect that now my run directory will be filled with files for each timestamp. Okay. Yeah, you can see now there is a lot of files, isomers fraction files, list of abundances that were calculated for each of these integration timestamps, 260, 61, etc., starting from 0 and up to the last cycle or integration timestamp 494. Okay. So I can show you that this computations with decay time equals 0 are useful because they provide these results show you can be used to see how abundances of a given isotope or element they change with time. For this, we would like to save all these files in some directory with a unique name. For this, you can use the script which is called copy output, which is in the run directory as well. So // which means the script in the current directory, copy data. If I execute it, okay, I check ls. Now there are no all these files anymore, but all these files now are written in this directory ppn run test. It has just some default name ppn run test. If I go to this directory ppn run test, you can see that all these files are now saved here. They're saved here with information about isotopes that were used in our nucleotide computations, which is included in this file isotope database.txt. Okay, this is an important file, but the script copy output will save this file as well, so you shouldn't care about this. Let me go back here. Okay. Okay, now let's keep in mind that we've created this directory, and let's go back to readme file. Okay. So I explained you almost everything in this first paragraph. So this with this bold font, I make a note, important note for you, that the option of positive decay time, say decay time equal 1 billion years, this option, along with option IO level equals 0, when there is no output on the screen. So these two options must be used in Monte Carlo runs. Okay. Because Monte Carlo runs, we are interested only in the very last computed integration time stable cycle, because we are interested in the final abundances. We are not interested to see how they change with time. Okay, we will talk about Monte Carlo runs next Monday, so therefore, please just keep in mind this note. Okay, so we discussed this, we discussed clean output and copy data scripts. Okay, that's it with this paragraph. Now the next paragraph also provides some useful information. It says that before starting multiple PPN runs, so multiple PPN runs, multiple here means that instead of starting just one PPN run, like I showed you with code ppn.exe, right? You can start simultaneously several such runs, say 10 of them, 12 of such runs. Okay, therefore the word multiple. So before starting multiple PPN runs, yeah, and you need to do multiple PPN runs when you compute data for the snake curve, and I will show you. Or you need also to start multiple PPN runs when you do Monte Carlo simulations. Of course, because if you just use a single PPN run, and in Monte Carlo runs you need to do at least 1,000 of them, then you will have to repeat your calculation thousands times. But if you run simultaneously say 10 pp runs, then instead of 1,000, you will need to do only 100 runs. Each of them will do simultaneously 10 individual runs, right? So therefore multiple. So and, this paragraph explains that before starting multiple pp runs, but after successfully executing the previous step, checking that ppn.exe principle works. So after successfully executing the previous step, change the value of the parameter inAnat equals 0 to inAnat equals 3 in the file ppnphysics.input. Okay, I will explain you what this parameter is used for. So let's go. This is in the file ppnphysics.input. Okay, let's go here. Now let's take ppnphysics as one input. Again, you don't see anything on the screen. Therefore, after that, click Ctrl F, and then 1 Shift G, like George. Okay, then you are at the beginning of the file. So here you can see I already have in template inAnat equals 3. So there are three useful values of parameter inAnat. inAnat equals 0. inAnat equals 0. What it does, let me show you. Okay, inAnat equals 0. Okay, so I will also ppn frame.in ppn frame.input, right? Okay. So now I'm going to change decay time back to 1 billion so that I don't have a lot of files in the output. Okay. Okay, and let me pay attention to this file network setup.txt. Let's check when it was created. It was created it was created actually when I copied this template directory. So the file network setup.txt, this is, as its name says, a network setup. So this file actually setups your nuclear reaction network. Okay, so it actually describes what nuclear reactions you're going to use in your nucleosynthesis computations. Okay, and if I go now back to ppnphysics.input, okay, and if I use the value of inAnat equals 0, this means that I ask the code ppn.exe to prepare a new network setup.txt file, to prepare a new nuclear reaction network, and immediately after that start computations of nuclear synthesis. Right? So therefore, in principle, for testing purposes, I'm supposed to use the value of inAnat equals 0. So therefore, this is what README files explains. inAnat equals 0. Okay. Yeah. So the next value of inAnat is inAnat equal 1. The value of inAnat equal 1 instructs ppn.exe code to create a new network setup.txt file, nuclear reaction network, and stop. Okay, and inAnat equal 3. Okay, inAnat equal 3 instructs ppn.exe code to not create a new network setup.txt file. Instead, use whatever network setup.txt file is available in the current run directory and just start nuclear synthesis computations. So switching these values is useful when you say, first of all, when you want to repeat calculations with the same network setup.txt file. You don't want to change them. Assuming that you have a network setup.txt file that you need. Then you just use the value 3, which means that the code will not create a new network. Okay. Or you just wanna say create a new network setup, then use value equal 1. Okay. But the value 3 is used when you need to do multiple calculations with the same network setup txt. Therefore, it was its value was actually in a net equal 3. Right? Okay, so now that we're here, this is explained, and also important that yeah, what I've just said, this is explained here. And also what's important is that Monte Carlo runs must use, because they use a large number, say 1000 of previously prepared network files with modified reaction rates. In Monte Carlo runs, actually, each of Monte Carlo runs, each of this 1000 or 1000 runs uses actually its own network. So, and because we need to use different networks, therefore, of course, Monte Carlo runs must be run with the value of net equal 3, which means that the code will not change a network. It will use whatever network is available for the run. Okay, so the next recommendation says that you should just check that your parent directory, that the parent directory of your PPN run has this symbolic link. So this is my run directory. I go to the parent directory outside and I check that, yeah, it has this link. Yeah, it does have this link. And pdata, this link, which is good. Okay. Okay, so now after this, we are ready to start multiple calculations, results of which will be used to make a snake curve. So for this, we need to use this notebook copy full series. Oh, sorry, run full series notebook. Explains we need just to copy this notebook from the iProcess tools notebook directory to our run directory, and use it to start multiple PPN runs for a range of constant neutron density specified in the notebook. Okay, so it's in iProcess tools. Okay, iProcess tools. Let me check it. Okay, in the subdirectories notebooks. Okay, so it's here, run full series Python notebook. So I go back to my run directory, which is here. Okay, and I copy readme files and structs. So I copy it from iProcess tools notebook. Copy iProcess notebooks, run full series, copy here. So now I have this notebook here. Okay, I go to my file manager. Okay, I go to iProcess sims to my run directory. And this is notebook run full series. I open it. Okay. So it says, the title says, run a set of ones on PPN computations for constant neutron densities from a given range of decimal logarithm neutron density values using this method. I mentioned you can, yeah, this method actually, this method, okay. To reach equilibrium once and uncapture nuclear symphonies. Okay, this method is described in this notebook. Okay, so now if I execute this, okay. Okay, so the next cell just prepares a range of decimal logarithms of neutron density that will be used in this multiple runs. And the next cell prepares this range, and you can check if this are neutron densities that you need. Okay, so therefore, so it says the set of PPN computations will be run for the following concentrated density. So this, are not decimal algorithm. This is just neutron densities. There will be 23 cases, 0, 1, 2, etc., 22, with neutron density starting from 10 to the 7 neutrons per cubic centimeter and increasing with 0.5 dex, 0.5 dex, okay, approximately, by a factor 3.16, up to 10 to the 18. So as this method on constant side is recommended to be used only up to neutron densities of order 10 to the 18. So 23 neutron densities, and the next and final cell of this notebook, it just starts with computations, okay, multiple. So if I will just start executing, you can see this black circle means that notebook is working. If I go back to my run directory, now you can see now there are 23 directories created with names. Those names run default. These names default is just a case name. Default means that in these computations I use default nuclear reaction rates for neutron capture reactions, which come from GINA reactive. Okay, so therefore default, but you can change this name for other cases. If you say change some reactions with respect to the default values, then you should change appropriately the name so that the name reminds you what reaction rates were changed. But in this case, it's just default. And you can see there are 23 directories. And if I execute the command top, it shows here, you can see we have a lot of ppn.exe codes running simultaneously here. And each of this code does the computation that I showed you before for its own neutron density from this list of neutron densities, okay? So it will take some time, I would say about 5-10 minutes, okay? 5-10 minutes. Okay, and while it's running, let me go back to the README file, okay, and show you the other useful notebooks. So the next notebook after this run full series notebook that is still running is called Analysis Outreach. And this notebook helps you to analyze results of individual PPN I-process nucleus into the simulations. Okay, so I'm going to show you how this notebooks work by analyzing the data that I saved, saved in the directory pp run test, right? pp run test, and this notebook uses output data that includes mass fractions for each integration time step. So therefore, data for this notebook should be produced with decay time equals 0. And I have such a case, I have such directory. So therefore, while this run full series notebook is working, let me show you how this analysis application notebook can be used. So I go to I-process tools notebook. And remember, I told you that here there are two notebooks with name analysis, but you should use notebooks which have the suffix outreach. Instead of analysis, use analysis outreach. Okay, this one. Okay, this one. So it says analyze results of PPN runs done using the branch, this one, of the Astra Hub of this shell. So now let me clean the output, previous output. Okay. Now let's execute the first cell with just populates namespace. Okay, the second cell is important here and in other outreach notebooks with suffixes outreach. In the second cell, or in the third, depends on the notebook, you will have to provide the name of your directory, right? So here, let me try to use my second name, Pavel Den, right? Where I recently created, you saw that directory ppn run test. Okay, so let's execute this. Everything else should work like this. So in next cell, we should select a method that was used to do calculations. Method 1 for this branch and construct size. So for method 1, we use and construct size method. And here, so the path to directory, it just uses the name of directory provided. Now ppn method 1 cases. So now here I should replace with the name that I have in my run directory, which is ppn run test, right? Let me check. Yeah. And then this ppn run test. Okay, ppn run test. So ppn run test. Okay, that's it. Okay, let's execute. Okay, now here it reads the output data that we produced. Okay, and now it says there are the following cases are available for individual analysis. Only one case number 0, therefore I have chosen it, I case 0. And this is the name of the case, then directly we can run test. Okay, so I executed this, now I execute this. Okay, and you can see that this plot shows how abundances, mass fractions, XY, the decimal logarithms of these isotopes change with time. So time is also taken decimal logarithm of time in years. Okay, it shows the neutron density that was used, decimal logarithm 13.5. Okay, this is what we used in our run ppn frame. Yeah. Yeah. And mass fractions, decimal logarithm is a function of decimal logarithm of time in years. Temperature was 200 million Kelvin. This is neutron exposure in inverse millibar. Okay. Also, we can make a plot of abundances as a function of cycle or integration time instead of time. Okay. Yeah. So you can see this cycle that I mentioned before, this just integration time. So, and the final cycle, you remember, 494. Also this case. Make a plot of undecayed isotopic abundances of heavy elements. So for you, it will take some time just to read all these comments and try to make these plots so that you will gain some experience with these computations before we'll do research. Okay. Now read solar elemental abundances in this present initial. Okay. While making a plot of elemental abundances for the solar, record the solar elemental abundances. Okay, like this. Okay. So this is a plot of final abundances, mass fractions, relative to their corresponding solar abundance, decimal logarithm, as a function of proton number. And you can see we have enhanced heavy element abundances for proton number above, say, 30, we have abundance relative to solar above 0, and they reach 3, which means they are 1,000 times higher abundances of these elements than in the sun. And this is a result of high process nuclear synthesis, which is a neutron capture process at specified neutron density, decimal algorithm neutron density 13.5, which means 3.16 times to the 10 to the 13 neutrons per cubic centimeter. In the file ppm_frame.input, of course, we can change this neutron density. We can use different value. Okay, but now we have this full series run, which automatically changes neutron density from the range of neutron density we provided. Yeah, let's just try to execute other cells in this. Okay. Okay, so now in some notebooks in the cells you can choose double elemental abundance ratio that you want to, for which you want to make a diagram. So here, as you can see, I have 3 types of diagrams. First, barium, lanthanum, lanthanum to europium, which means there will be a diagram made of barium to lanthanum elemental abundance ratio on the x-axis versus to lanthanum to europium elemental abundance ratio on the y-axis. Okay, and if you want to change this to barium to lanthanum versus barium to europium instead of lanthanum to europium, you should uncomment these lines and comment these lines. And the third option available so far is strontium over yttrium along x-axis versus yttrium over zirconium, elemental balance ratio over y-axis. So now let's just keep barium to lanthanum versus lanthanum to europium. Let me execute this. Okay. So as you can see, as I said, this is a diagram of barium over lanthanum elemental abundance ratio. So square brackets, as I said last time, this is a standard stellar spectroscopic notation, which means square brackets here mean this elemental abundance ratio in the star, its decimal logarithm minus the decimal logarithm of the same ratio for the sun, okay, versus lanthanum to europium. And this point corresponds to the final abundances in our case run, which is in the directory ppn run test, which has neutron density logarithm 13.5, and this color green here on the color bar shows that indeed these calculations correspond to neutron density 13.5. We could include in this notebook at the beginning not just one, but several cases for different neutron densities, in which case we would have here just several data points. Okay, but so far I have just one. Plot. This is a similar plot, but it shows the x elemental abundance ratio of barium over lanthanum as a function of neutron density. Yeah, of course, now I have just one neutron density, which is approximately 13.5. So therefore, this plot is not that informative. Okay. Now make a plot of chat of nucleids. This is a useful plot. Okay. Okay. So this is a plot of a chat of nucleids. So here we have neutron number increasing to the right, proton number increasing upwards. Okay. And here we have solid boxes correspond to stable isotopes. Boxes without solid boundary correspond to unstable isotopes. Red lines correspond to magic proton neutron numbers. So magic numbers are 50, 82 for neutrons, and for protons here 50. Okay. which means along lines, red lines of magic numbers, we have anomalously stable isotopes. And as a result, you can see here we have accumulation of isotopes. So the redder color means high abundance, which means we have here accumulation, because these isotopes are stable. So they're more stable than neighboring isotopes. Okay? And this diagonal line with solid boxes is called the value of stability because it includes stable isotopes. And while the S process, slow neutron capture process, goes along the boundary of the value of stability here, I process goes further away in neutron number from the value of stability to the right. And its width to the right, of course, is determined by the neutron density. If I use the higher neutron density, say 10 to the 15 or 10 to the 16, the width of this band of I process would be larger. So Y process would continue, say, up to here. It would be larger. Okay. So therefore, such chart of nucleides is also very informative. Okay. Okay. Yeah. So the next cell, as the title explains, prepares some arrays for some plots. But the comment in parentheses says this takes a long time, therefore skip the second, third, and fourth cells if you already executed it before, or if you are not interested in this right now. So therefore, skip the second, third, and fourth. So we still have to execute the first one in any case because it provides this one. It specifies this one. And let's skip second, third, and fourth. Okay. Now let's go here. And now we're going to compare results of our computations with observational data. First, we are going to choose a CMP I star, carbon enhanced metal core star, with signatures of I process in its atmosphere. Okay, so next cell help us to choose this star. First, we see this is a list of available CMP I stars. And now I'm going to select the star with number 13, which will be this our favorite star, by the way, CS 31/62 minus 50, number 13. Okay, so I choose this star. You can choose another star. Now this provides available abundances for this star. Okay, elemental abundances. So therefore, this number in the second column gives proton charge number. For instance, 56 proton charge number corresponds to barium, 63 to europium. Okay, this is its metallicity. The metal core, carbon enhanced metal core stars, and iron to H ratio metallicity is minus 2.4. For the sun, of course, iron to H square brackets is 0. So this star is less abundant in iron than the sun by a factor of 200, approximately 200. Okay, and now next plot will compare results of our computations with the observed abundances in this case in our star, and we use here two methods. These comments explain where you can find the description of the methods. Here we use the so-called pinned element, and here I chose for the pinned element 63, which is europium. Okay, you will read this later. Let me just execute this. Okay, so now this comparison between computations and predictions. There is a very good agreement, as you can see. And this is europium, and you see the predicted abundances is exactly equal to the observed europium. This is what pinned abundance means. So we just fit the predicted in the europium abundance And all other abundances are just calculating according to the amount of shift that we used to pin European abundance. But given that all observed abundances are matched by predicted ones very well, maybe yeah, except of Presidium, this one. Yeah, but it's a different story. So there is a very good agreement. So the next cell uses another method of comparison between predicted and observed abundances, which uses dilution coefficient. It's described, as this comment explains in this paper, so I'm not going to talk about this method. You just adjust dilution coefficient here. Actually, dilution coefficient here, let's say 2%, it gives the share of your computed abundances, I-process abundances, their share in the mixture with initial abundances. So dilution coefficient 2% means that you mix 2% of your computed abundances with 98% of initial abundance unchanged. And you can, of course, for different stuff, you have to adjust dilution coefficient and see if you can reach agreement between theory and observations for different dilution coefficients. Okay, so there is also very good agreement using this method, which is not surprising. Both methods should give consistent results. Okay. Okay, so other cells are not that important, except that the very last cells, as this comment explained, they make plots of reaction rate fluxes. And as I mentioned before, in order to make these plots, you will need to run ppm exec code with the value of flux option equal 1, only for these cases. Otherwise, use the value equal 0. Okay, now let's go back to our notebook. The calculations are finished. We can also check in our run directory top. So there are no calculations anymore. And all results are stored in these directories. Okay. Now, in order to make the snake curve, okay, as a README file, this is your main instruction document, README outreach. Okay. So in order to make a snake curve, now we need to use this notebook. It seems it has a long name. But this comment says this notebook reads in a set of specified ppm results obtained for constant different densities. Okay. For example, those from the first step that we already done the first step, and saves the predicted elemental abundances in a pickle file. This one that is used by the other analysis notebooks. Okay. And the next notebook plot. It makes the plot of multi-element abundance ratios and makes a plot of the snake curve. So therefore, I'm going to show you these two notebooks. One that uses results of multiple runs that we've just done, and the second notebook that makes a plot. So let me go here. All notebooks are in our process tools notebooks. So README this ones. We need one with with outreach, this one, and after that plot. Okay, plot outreach, this one. Okay. So let's go to README, this one. Read results of multiple data assets at Middle Months dictionary. Okay. Okay. So you can try to use this notebook during this week at home. I'm not going to do this because it takes a long time. Not all cells, but the cell that reads all those 23 runs, it takes a long time. So I'm not going to waste this time. I already have results produced with this notebook in my second directory with name Pavel. I will show you these results. So therefore, let me just switch to my other directory. So I'm going to close this notebook, okay, and also README. But I go now to my second directory where I already have these results. I obtained them when I tested all these computational tools. Okay, okay, I'll reach Pavel. Okay, I process things. I process tools and notebooks, and now plot outreach. Okay. So now this is notebook that plots a snake curve and some other results, including results from Monte Carlo simulations that we don't have yet. We will talk about Monte Carlo simulations next Monday, as I said. So now let me just show you how to make a snake plot based on the results that we obtained in those this run full series, run series. Okay, and before you, of course, go to this plot notebook, you should have run the notebook read with long name. This one, this notebook, and prepare data for the snake curve. Okay, I'm skipping this step because it takes maybe 20 minutes, maybe 30 minutes. So I don't want to waste this time. And I go directly to the plotting node. Okay, and we are almost finished. Let me just execute the cells. The first cell in each notebook just populates the space with Python functions in directive namespace. And this is just, let's check where I am. I am in Pavel, right? Again, you see in this case, this is the third cell. Don't forget to provide in cells like this the name of your directory. For instance, John Stevens, whatever. Here I have Pavel, not Pavel Den. This is my second directory. Okay, everything else should just work almost automatically. Okay, now we have reached this cell, and again here we can choose between three diagrams with different elemental balance ratio. Let me just choose barium to lanthanum versus lanthanum to iridium. For this, I have to comment these ones, right? These ones. I have to comment them. That's it. Okay. And this cell, after you have chosen what elemental balance ratio you want to plot, yeah, it makes this diagram where it plots so far only observational data. So each of these triangles corresponds to one's CMP I star, not only CMP I star, but CMP carbon enhancement of post star from the catalog GINA base catalog. Here, this is here from the GINA base catalog. Okay, and as you can see here, orange triangles correspond to CMP I stars. This is the stars that we study, okay, CMP I stars. And blue triangles, they were classified in the catalog as CMP S stars, assuming that they have abundances produced in S process, which we think is not quite correct, but we'll talk about this later. Okay, and now our task is to add to this plot a snake curve, right? Let me divide snake curve obtained with that notebook read, it has a long name, with this notebook, based on the calculations done with run full series, this notebook, okay? So now let's check where we have, you see, the next cell adds contour lines to the plot from Monte Carlo simulations. We don't have them yet, so therefore I'm going to skip this cell. Don't execute each cell. First read what this cell does. And if you know that you have not done yet Monte Carlo calculations, just skip this cell. Okay, and now the snake curve is just here, plot simulations, and you can see the first cell here in this section will read this dictionary pickle file that was prepared in the previous notebook that I have not executed because it takes a long time, but you will try to execute it at home, okay, based on your calculations. So now it reads it. And now let's make a plot. Yeah. Okay. So now we can see this is the snake plot. I was telling you about, right? And so now let's continue executing this. Now this is the snake plot overplotted over observed abundances, right? And we can compare our calculations for constant neutron densities calculations with observational data. And I think that's it. Don't execute other cells. So now about your assignment, okay, homework assignment for this week till the next Monday. I ask you to try to repeat this computations and notebook analysis that I told you about, and reproduce this plot here, right? Yeah. This is not the only thing that I want to ask you about, right? So we have 8 minutes left, and I have enough time to explain you what I would like you to do. So remember that this snake plot was obtained with a default neutron capture reaction rate, right? Default nucleate rates. Okay? Therefore, in my run directory, I had these directories with name default. Okay? But now the most interesting problem is when we want to change some of the rates, because these results of these computations, they are based, as you remember from analysis notebook, the results depend on reaction rates, on unstable isotopes, right here. If I take isotopes here to the right from the value of stabilities, they are all unstable, which means that for them, there are no experimental measurements of neutron capture reaction rates. And instead, theoretical predictions are used for these reaction rates. So therefore, this means that we cannot say that these reaction rates are correct. In fact, the uncertainty can be a factor of 10 up or down. We don't know yet. So therefore, an interesting experiment that I want to ask you to do is to change some of individual rates for unstable isotopes and repeat calculations and make a plot of snake curve with changed reaction rates. Okay, how to change reaction rates? This is very easy. When you go back to your run directory, remember when you open ppn physics .input, remember this parameter inANAT equal 3, right? So first you run with inANAT equal 1, inANAT equal 1, right? Okay, you run ppn.exe with inANAT equal 1. And so this text explains that no nucleosynthesis computations were done. Instead, there was just this file, network setup.txt created. We can see it was created right now. It was created 23:25. Now we have 25. 23 corresponds to some other time zone, but 25 minutes to do. So we've just created this network setup.txt file. Now I go back to ppn physics, okay, and let's not forget to change parameter inANAT to 3. 3 means we ask the code to use whatever network setup.txt file which is available in the current directory. But now I'm going to change rates of some reactions in this file. So I open network setup.txt, right? Okay, and on this week, I will ask you to change 3 neutron capture reaction rates. Okay, I will send you after our online meeting. I will send you an email providing information for reactions that I ask you to change and the values that we should use. Okay, there will be three reactions. I will just show you as an example just one reaction, which is barium 139 and gamma. So first, when you have opened this file, you just search for this reaction. So in the Vim editor, I just press slash, then barium 139. The names of isotope have 5 positions. So barium 139, doesn't have spaces. Okay, and I continue to search until I will find the reaction barium 139 and gamma. Okay, I just continue search. Okay, now I found, as you can see, this is barium 139, neutron, gamma. The product is barium 140. And this column says that this is reaction N gamma, barium 139 and gamma. And for each reaction, the column before the last one, this column, contains the so-called multiplication factors. And when we use default rates, of course, multiplication factors are all equal to 1. 1 means when I multiply the rate by multiplication factor, it doesn't change, which means use default rates. But now I want to increase this rate, barium 139 and gamma, by a factor of 2. Remember, I will send you email with a list of reactions and the multiplication factor. So you just replace 1 by 2. You see, I replaced 1 by 2 for barium 139 and gamma. That's it, just for one reaction per time. Now I save this file. And remember, important is that in PPN physics, I use in a net equal 3, which means don't replace network setup.txt file. Use whatever file is available. In this case, the code will use network with increased reaction barium 139 and gamma by a factor of 2. Okay, and now you just run the code. You either run one individual code or you run full series. They will all use barium 139 and gamma reaction rate increased by the factor of 2. Okay, so I will ask you to do such changes for 3 reactions. I will send this information via email. Okay, and repeat these calculations and produce 1, 2, 3, 4 snakes plot. There will be 3 changes, but one snake plot will be for 2 changes, for changes in 2 reaction rates. I will explain this in my email. Okay, that's it for today. Yeah, it's right on time. I stopped sharing my screen, and I hope that you are still there. Can you still hear me, guys?
Yeah, thank you.
Yes.
Okay. Yeah.
I have
questions.
Yeah, I have a small question. When running the code in the what's the file? The PPN frame input file.
Yeah.
Should we change the decay time to 1 to the 9 or use 0?
Yeah, I see. Okay. Yeah, good question. Just a second. Just a second. Let me start sharing my screen again. Okay, just a second. Okay, so this is my run directory. Okay, let me go to one of these default run directories. Okay, and check. Yeah, you see, each of these multiple run directories have a lot of output files, right? Which means decay time was 0. Decay time was 0. Yeah.
Okay, perfect. Thanks.
Yeah, just a second. Let me check this. Let me check this with this file. This is a good question. I just don't remember. Okay, so this is the notebook that reads all these directories, okay, to make data for snake. Okay, I didn't execute it. Yeah, you can see it here. This notebook read seems long name. It uses as input those directories with default name. So they have a lot of output data, which means decay time is 0. Actually, decay time non-zero positive is used only for Monte Carlo calculations, only for Monte Carlo. Okay.
Okay, I get it. Thanks.
Only for Monte Carlo. And README file explains this. Because for Monte Carlo calculations, you need to keep just the very last computed time step. But here, when you compare with observational data, you need abundances for all time steps, okay, for all time steps. And by the way, Python functions that are used in these notebooks, as well as an analysis notebook, they actually do decay themselves, those functions. Okay, they calculate decay abundances. If this is they calculate decay abundances. So don't care about this. Okay, so you should use decay time positive, say 1 billion years, only for Monte Carlo calculations. That I think this is a short, simple answer. Okay? More questions? Okay, if not, I'm stop recording, and I hope to see you next Monday. I will send you email as well as a link to this video, so you can watch this video again. Okay, I stop recording.